Hello there and welcome to Calm Science. I am so glad you are here. Take a moment to find a comfortable position, one that feels effortless and soft. Let your body grow heavy, supported by the surface beneath you. Allow your breath to find its own gentle rhythm, slowing on its own time. There is nothing to do right now and nowhere else to be. The day is done. Tonight, we will drift toward the largest planet in our solar system. A world of swirling clouds and quiet moons. We will explore the great gas giant Jupiter. We will float through its colorful bands, witness its ancient storms, and visit its family of fascinating moons. There is no need to keep track of the details. You can fade in and out of listening. The ideas will be here, soft and simple, whenever you return. Let your mind idle, and let us begin our slow journey to Jupiter. The scale of Jupiter is almost beyond comprehension. It is a world of immense presence in our solar system. If you were to gather all the other planets, from Mercury to Neptune, and combine them into one, Jupiter would still be more than twice as massive. It is a giant among giants. You could fit all the other planets inside of it with room to spare. In terms of volume, more than 1,300 Earths could nestle comfortably within its spherical shape. Its gravity is so powerful that it gently tugs on every other body in the solar system, including the Sun itself. In this way, it anchors our planetary family. Let the body grow heavier as the mind stays simple. From a distance, Jupiter looks like a solid marble, but it has no solid surface to stand on. It is a gas giant, composed almost entirely of the same elements that make up a star. The vast majority of the planet is hydrogen, with the next most abundant element being helium. These are the lightest and simplest elements in the universe. Deep within its atmosphere, the pressure becomes so immense that these gases change into exotic forms of liquid. But there is no clear boundary where the gas ends and the liquid begins. Only a gradual, seamless transition. As you rest, this giant world turns, a colossal sphere of gas and cloud. Hold the shape of that thought lightly and return to ease. Despite its enormous size, Jupiter spins faster than any other planet. A day on Jupiter, the time it takes to complete one full rotation, is just under 10 hours. This rapid spinning has a profound effect on the planet's shape and its weather. The centrifugal force generated by this speed causes Jupiter to bulge at its equator and flatten at its poles. It is not a perfect sphere, but an oblate spheroid. This fast rotation also drives the planet's powerful jet streams, stretching its clouds and storms into the long, distinctive bands that circle the globe. Through a soft lens, the planet is a blur of constant, unhurried motion. You can breathe a little deeper and allow the thought to drift. Jupiter's atmosphere is a canvas of beautiful, muted colors, swirled into distinct bands. These bands are known as zones and belts, and they run parallel to the equator. The lighter colored bands are the zones, where gas is rising and cooling, forming high-altitude clouds of ammonia ice. The darker bands are the belts, where gas is sinking and warming, revealing clouds of different chemical compositions from deeper layers. These alternating currents of rising and falling gas are driven by incredibly fast winds, some blowing at more than 500 kilometers per hour. In a calm rhythm, these bands remain stable for years, a portrait of organized, large-scale weather. Settle back into the soft pace of night. The soft colors we see in Jupiter's clouds, The pale yellows, rusty oranges, and soft browns are the result of subtle chemical impurities. The main clouds are made of ammonia, ammonium hydrosulfide, and water, which are all white or colorless on their own. Scientists believe that trace elements, often called chromophores, are responsible for the planet's palette. These could be compounds of sulfur, phosphorus, or carbon, churned up from deeper, warmer layers of the atmosphere. When these chemicals are exposed to ultraviolet light from the sun, they undergo a chemical reaction that gives them their distinct hues. As the pattern repeats, these colors paint the swirling storms and jet streams. Return to the easy rhythm of your breath. Jupiter does not have one uniform cloud deck, but rather several layers stacked on top of one another. The highest layer, the one we see most clearly, is composed of frozen ammonia ice, just like the zones of rising gas. Beneath this foggy white layer, astronomers believe there is a second deck of clouds made of ammonium hydrosulfide crystals. This layer is likely responsible for some of the brownish and orange colors. Deeper still, there is a third layer, a dense deck of clouds made of liquid water and water ice, much like the clouds on Earth. Most of this complex three-tiered structure is hidden from our view. Beneath the surface, the planet holds its layered secrets. Let that settle like dust on a quiet floor. The Great Red Spot is Jupiter's most famous feature, an ancient swirling storm larger than our own planet. This colossal anticyclone, a high-pressure system, has been observed for at least 200 years and possibly much longer. Winds at its periphery blow at staggering speeds, but the center is relatively calm. It rotates counterclockwise, taking about 6 Earth days to complete one full turn. For centuries, it has been a prominent and enduring landmark in Jupiter's southern hemisphere. But in recent decades, astronomers have noticed it is shrinking. The storm that was once wide enough to fit 3 Earths side by side is now closer to the width of one. Over time, even this ancient giant is slowly changing. Rest in the steady comfort of this moment. The exact reason for the Great Red Spot's distinctive brick red color remains a gentle mystery. The storm is a high-pressure system, which means it dredges up material from deep within Jupiter's atmosphere. Scientists theorize that chemical compounds, normally hidden far below the upper cloud tops, are brought to high altitudes by the storm's powerful updrafts. Once there, they are exposed to the sun's ultraviolet radiation. This solar energy might trigger chemical reactions, transforming these colorless compounds into the reddish polymers that give the storm its famous hue. It is not in pigment, but a chemical reaction, painting the storm from above. From a distance, it glows like a slow burning ember. Let your shoulders drop and the jaw unclench. The Great Red Spot is not the only long-lived storm on Jupiter. The planet is home to many other vortices, most of them appearing as white or brown ovals. In the late 1990s, 3 large white ovals in the southern hemisphere merged to form a new storm. This storm, about half the size of the Great Red Spot, is now known as Oval BA. For a few years, it turned the same reddish color as its famous cousin, earning it the nickname Red Spot Jr. Since then, its color has faded back to a pale white. These storms can last for decades or even centuries, drifting through the jet streams like boats on a vast, wide river. In this quiet corner, the weather patterns are measured in lifetimes. Feel the simple ease of being here. Deep within Jupiter's water cloud layer, immense lightning storms rage. But this lightning is different from what we experience on Earth. On our planet, lightning tends to originate from water clouds in the lower atmosphere. On Jupiter, the lightning seems to be born from clouds containing a mixture of ammonia and water. Scientists propose a mechanism involving mushballs, a kind of slushy hail made of ammonia water ice. These mushballs fall, carrying electrical charge downward, while ice crystals lofted upward carry the opposite charge. This separation of charge can trigger a shallow lightning flash, high in the atmosphere. With unhurried steps, the planet's storms show their unique character. Rest in the quiet that follows. When NASA's Juno spacecraft flew close to Jupiter, it detected lightning flashes that were small but incredibly frequent, especially near the poles. These flashes, known as shallow lightning, occur in the upper part of the atmosphere, much higher than where Jupiter's main thunderhead clouds are thought to be. The flashes are sometimes only a few kilometers in size, but they happen many times per second. This suggests a different kind of storm process than the large, concentrated thunderstorms we know on Earth. It is more like a constant, gentle crackle of energy in the high clouds. Under quiet skies, the planet quietly sparks and glows. Let the thought soften at the edges and fade. Jupiter possesses the most powerful auroras in the solar system. Like the auroras on Earth, they are created when charged particles are guided by the planet's magnetic field and strike atoms in the upper atmosphere, causing them to glow. Jupiter's auroras, however, are hundreds of times more energetic and they never cease. They form a permanent, shimmering oval of light around each of the planet's poles, glowing brightly in ultraviolet light. These beautiful dancing curtains of energy are a constant feature, a sign of the immense power hidden within the planet's magnetic field. Along a steady path, energy flows and gives off a soft light. Nothing urgent here, only a slow and steady pattern. Jupiter's magnificent main auroral oval is not its only light show. The planet's magnetic field is so vast that it interacts with its largest moons. As the moons Io, Europa, and Ganymede orbit the planet, they leave a trail of charged particles. These particles are swept up by the magnetic field and funneled toward Jupiter's poles. When they hit the atmosphere, they create their own auroral footprints, small, dedicated spots of light that glow just outside the main oval. These footprints move in sync with the moons, a faint, visible echo of their distant dance. In the gentle background, the moons leave their mark on the mother planet. Allow the day to fall away now. Recent observations from the Juno mission have revealed a strange and beautiful pattern at Jupiter's poles. Unlike the banded zones and belts that dominate the rest of the planet, the polar regions are home to swirling, persistent cyclones. At the North Pole, one large cyclone sits at the very center, surrounded by 8 smaller cyclones, all spinning in a stable, geometric arrangement. The South Pole has a similar pattern, with one central storm and 5 others arrayed around it. These cyclones are enormous, each one thousands of kilometers across. They have remained in this strangely geometric formation for years. In quieter hours, we find patterns of unexpected order. Let that idea rest for a moment before we move on. Deep below Jupiter's cloudy exterior, the pressure and temperature climb to unimaginable levels. About a quarter of the way down to the center, the hydrogen gas is compressed so intensely that it transforms into a substance that does not exist on Earth. It becomes liquid metallic hydrogen. In this state, the hydrogen atoms are stripped of their electrons, which can then move freely, much like the electrons in a metal. This vast planet-sized ocean of metallic hydrogen is what generates Jupiter's immensely powerful magnetic field. As the planet spins, the motion of this conductive fluid acts like a giant dynamo. Beneath the surface, the planet holds an ocean of liquid metal. Let your breathing find a slower pace. Within the layer of liquid metallic hydrogen, something interesting is thought to happen with the helium. Under the extreme pressure, the helium, which does not mix well with metallic hydrogen, is believed to condense into droplets. These droplets, being denser than the surrounding hydrogen, would slowly rain down toward the planet's core. This process, known as helium rain, would release gravitational energy, which in turn generates heat. This is one of the reasons why Jupiter radiates nearly twice as much heat into space as it receives from the Sun. The planet is not just cooling from its formation, it is actively generating its own internal heat. With simple patience, the planet's inner workings reveal themselves. Hold only the calm and let the rest drift. For a long time, scientists believed that Jupiter must have a small, solid, rocky core at its very center, a seed around which the gas giant originally formed. But data from the Juno mission has painted a more complex and gentle picture. Evidence suggests that Jupiter's core is not a solid, compact ball. Instead, it seems to be a fuzzy or dilute core. The heavy elements, like rock and ice, are not neatly separated at the center. They are mixed with hydrogen over a vast region, perhaps up to half of the planet's radius. This suggests that the early Jupiter may have experienced a giant impact that stirred its core. With the same easy pace, our picture of the planet softens. Feel the calm gather around you again. In fact 18. As we've learned, Jupiter emits far more energy than it absorbs from the distant Sun. This internal heat is a remnant of its formation, 4.5 billion years ago, as well as the ongoing process of helium rain. This means the planet is slowly but continuously cooling and contracting. The contraction is incredibly slow, only about 2 centimeters per year, a rate far too small to see. But over millions of years, this gradual shrinking releases a tremendous amount of gravitational energy, which is converted into heat. This heat then slowly radiates out from the top of the atmosphere. As the night settles, the giant planet gently cools. Let the thought soften at the edges and fade. Jupiter is surrounded by an immense invisible structure called a magnetosphere, generated by the ocean of liquid metallic hydrogen in its interior. Jupiter's magnetic field is nearly 20,000 times more powerful than Earth's. If our eyes could see it, the magnetosphere would appear as a teardrop-shaped bubble, so enormous it would be the largest object in the solar system, appearing several times wider than the full moon in our sky. It stretches so far that it almost reaches the orbit of Saturn. Elsewhere in this picture, an invisible force shapes the space for millions of kilometers. Rest in the quiet that follows. The immense magnetosphere of Jupiter traps charged particles from the solar wind and from its own moons, creating the most intense radiation belts in the solar system. These belts of high-energy particles are similar to Earth's Van Allen belts, but they are thousands of times more powerful. This radiation is so intense that it would be instantly lethal to an unprotected human, and it poses a significant danger to any spacecraft that dares to get close. To protect its sensitive electronics, the Juno spacecraft is housed in a titanium vault and follows a long, looping polar orbit to minimize its time spent within the most dangerous regions. Without any hurry, we learn to navigate this invisible hazard. Set the idea down and feel the weight release. Jupiter's powerful magnetic field and its rapid rotation, combine to produce strong radio emissions. Some of these are so powerful they can be detected on Earth with simple amateur radio telescopes. These radio waves are generated by electrons spiraling at high speeds along the magnetic field lines, a process called synchrotron radiation. The signals rise and fall in a steady rhythm, tied to the planet's 10-hour rotation. By listening to this cosmic static, astronomers in the 1950s first deduced that Jupiter must have a powerful magnetic field long before any spacecraft had visited it. Across these vast scales, the planet sends out its own faint rhythmic broadcast. You can breathe a little deeper and allow the thought to drift. Jupiter is the king of a miniature solar system, with a retinue of at least 95 known moons. The 4 largest and most famous of these are the Galilean moons, discovered by Galileo Galilei in 1610. These are Io, Europa, Ganymede, and Callisto. Each one is a world in its own right, with its own unique geology and character. Their discovery was a pivotal moment in history, as it showed that not everything in the heavens orbited around the Earth. It was the first clear evidence of a center of motion other than our own planet. With steady breath, we can appreciate this family of worlds. Let the body be held by what supports you. Io is the innermost of the 4 large Galilean moons, and it is the most volcanically active body in the solar system. Its surface is covered with hundreds of volcanoes, some of which are constantly erupting, spewing plumes of sulfur and sulfur dioxide hundreds of kilometers into space. This volcanic activity is not driven by internal heat, but by a process called tidal heating. As Io orbits Jupiter, the immense gravity of the planet, along with the smaller regular pulls from Europa and Ganymede, causes Io to be constantly stretched and squeezed. This friction generates enormous heat, melting its interior and powering its endless eruptions. In this quiet corner, a moon is kept hot by the pull of gravity. Allow the mind to idle in gentle space. The surface of Io is a vibrant, colorful canvas, painted by its constant volcanic activity. It has no impact craters because any that form are quickly buried by fresh lava flows and layers of sulfur. The landscape is a patchwork of yellows, reds, whites, greens, and blacks. These colors are all different forms of sulfur and its compounds, which change color depending on their temperature. The blackest areas are the hottest, freshest lava flows, while the yellows and whites are cooler deposits of sulfur dioxide frost. The world is constantly repainting itself, erasing its history with every new eruption. As you rest, imagine a world of quiet, colorful change. Settle back into the soft pace of night. Despite its small size, Io has mountains taller than any on Earth. Some of its peaks rise to altitudes of over 17 kilometers, more than twice the height of Mount Everest. These mountains are not volcanoes, but rather tectonic structures. They are created as the planet's crust is compressed and thrust upward. Unlike the mountains on Earth, which form at the boundaries of tectonic plates, the mountains on Io are scattered across its surface in a more random pattern. They are islands of stability in a sea of constant volcanic change, ancient blocks of crust that have been lifted and tilted by the immense stresses within the moon. From a distance, they are silent peaks on a restless world. Nothing urgent here, only a slow and steady pattern. Io's volcanic plumes beat a thin, tenuous atmosphere composed mainly of sulfur dioxide. This atmosphere is not permanent. Most of it is created by the constant outgassing from volcanoes, and it is just as quickly lost to space. Jupiter's powerful magnetosphere sweeps past Io, stripping away about 1,000 kilograms of material every second. This material, mostly ionized sulfur and oxygen, is then caught in the magnetic field, forming a donut-shaped cloud of particles that surrounds Jupiter. This structure is known as the Io plasma torus. It glows faintly in ultraviolet light and is a major source of the charged particles in Jupiter's radiation belts. In the slow turn of the planet, a moon creates its own ring of light. Let your shoulders drop and the jaw unclench. Europa, the next Galilean moon out from Jupiter, is a world of incredible smoothness and light. It is slightly smaller than Earth's moon, and its surface is one of the brightest in the solar system. It is covered in a shell of water ice, which reflects sunlight like a vast frozen plain. The surface is also remarkably young and free of craters, suggesting that it is constantly being renewed from below. It is crisscrossed by a complex web of long linear cracks and ridges, known as lineae. These features give the moon the appearance of a cracked eggshell. Through a soft lens, Europa is a world of pale, quiet beauty. Feel the simple ease of being here. Beneath Europa's shell of ice, there is strong evidence for a vast, global ocean of liquid salt water. The evidence comes from several sources. The moon's smooth, crater-free surface suggests a liquid layer below that can fill in any impacts. The crisscrossing lineae look like cracks in a floating ice sheet, being pulled and flexed by Jupiter's tides. Most compellingly, data from the Galileo spacecraft showed that Europa has a weak, induced magnetic field. This is best explained by a salty, electrically conductive ocean interacting with Jupiter's main magnetic field. This hidden ocean could contain more than twice the amount of water in all of Earth's oceans combined. Beneath the surface, a vast, dark ocean waits. Let that idea rest for a moment before we move on. The reddish-brown streaks that stain Europa's icy surface may be a clue to the composition of its hidden ocean. Scientists believe that these lines and mottled patches, called chaos terrain, are places where the ocean water from below has welled up and come into contact with the surface. The colors thought to be from salts, like magnesium sulfate, that have been bombarded by radiation from Jupiter's magnetosphere. If this is true, then studying the composition of these colored areas could tell us about the chemistry of the water in the ocean below. It is a way of tasting the sea without ever having to drill through the ice. Along a steady path, the surface reveals clues about the deep. Return to the easy rhythm of your breath. In recent years, the Hubble Space Telescope has detected evidence of great plumes of water vapor erupting from Europa's surface. These plumes appear to be transient, occasional bursts that shoot hundreds of kilometers into the sky before falling back down. They seem to originate from some of the warmer, more active regions of the ice shell. If these plumes are confirmed, they would offer a tantalizing opportunity. A future spacecraft could fly through one of these plumes and sample the water directly from the subsurface ocean, analyzing it for its chemistry and, just maybe, for signs of life. As the pattern repeats, the moon exhales its secrets into space. You can breathe a little deeper and allow the thought to drift. The existence of a vast liquid water ocean, combined with heat from tidal friction and a potential supply of chemicals from the seafloor, makes Europa one of the most compelling places in the solar system to search for life. Life as we know it requires three key ingredients: liquid water, a source of energy, and the right chemical elements. Europa appears to have all three. Any life in its ocean would have to exist in total darkness, perhaps clustered around hydrothermal vents on the ocean floor, similar to the ecosystems found in the deep oceans of Earth. We do not know if anything lives there, but the possibility remains. In this quiet corner, we find the potential for a hidden biology. Let the thoughts soften at the edges and fade. Ganymede is the third Galilean moon and the largest moon in our entire solar system. It is bigger than the planet Mercury and is the only moon known to have its own internally generated magnetic field. Its surface is a tale of two terrains. There are ancient, dark, heavily cratered regions, and there are younger, lighter, grooved terrains. The dark areas are thought to be the moon's original crust, dating back billions of years. The lighter areas are where the crust has been stretched and fractured and possibly flooded with water from below, which then froze into clean, bright ice. Over time, the moon has reshaped parts of itself. Rest in the steady comfort of this moment. Like Europa, Ganymede is also believed to have a subsurface ocean of liquid salt water. But on Ganymede, this ocean is thought to be much deeper, buried beneath a very thick crust of ice, perhaps 150 kilometers thick. Evidence for this ocean comes from the way Ganymede's own small magnetic field interacts with Jupiter's larger one. Furthermore, scientists now believe the ocean may not be a single layer. It could be a stack of multiple oceans, separated by different phases of ice that form under extreme pressure. Imagine a club sandwich of ice and water, stretching deep into the moon's interior. Under quiet skies, even a frozen world can hold layers of liquid. Feel the calm gather around you again. Ganymede's most remarkable feature is its intrinsic magnetic field. It is the only moon in the solar system that generates its own magnetosphere, like a miniature planet. This magnetic field is likely generated by a molten iron core, swirling and convecting deep within the moon. This creates a small protective bubble that punches a hole in Jupiter's much larger magnetosphere. As Jupiter's field sweeps past, it interacts with Ganymede's, creating its own auroras, curtains of glowing gas in the moon's thin atmosphere. They are a visible sign of the moon's hidden dynamic heart. Without any hurry, we see a moon with the heart of a planet. Hold only the calm and let the rest drift. Callisto is the outermost of the Galilean moons, and in many ways it is the simplest. Its surface is the oldest and most heavily cratered in the solar system, a frozen, quiet record of billions of years of impacts. Unlike the other Galilean moons, Callisto shows very little evidence of geological activity. There are no large volcanoes or tectonic features. It seems to have been geologically quiet for almost its entire history. Its dark, icy surface is covered in a blanket of fine dust left behind as ice slowly sublimates into space. From a distance, it appears as a dark, pockmarked ball, a static museum of the early solar system. Allow the day to fall away now. One of Callisto's most prominent features is Valhalla, a gigantic multi-ring impact basin. It is one of the largest impact structures in the solar system, with its outermost ring stretching nearly 4,000 kilometers across. The impact was so enormous that it didn't create a typical crater. Instead, the shock waves rippled outward through the icy crust, creating a series of concentric rings, like the ripples in a pond after a stone is thrown. But these ripples froze in place billions of years ago. The center of Valhalla is smoother and brighter, as the initial crater has slowly flattened over eons. In the gentle background, even cataclysmic events can settle into a quiet form. Let your breathing find a slower pace. Beneath its ancient icy surface, Callisto may also harbor a liquid water ocean. The evidence is more subtle than at Europa or Ganymede, but measurements of Callisto's magnetic field show that it seems to respond to changes in Jupiter's field, which suggests the presence of an electrically conductive layer, like salty water. If it exists, this ocean would be very deep, buried under at least 100 kilometers of solid ice. Because Callisto has less tidal heating, this ocean would be very cold and possibly less hospitable to life. It is a world that is almost, but not quite, completely frozen in time. Elsewhere in this picture, we find another possibility of a hidden ocean. Let that settle like dust on a quiet floor. Jupiter has a faint, almost invisible ring system. It is so tenuous that it was not discovered until 1979, when the Voyager 1 spacecraft flew past the planet. Unlike Saturn's bright, glorious rings of water ice, Jupiter's rings are made of fine, dark dust particles. These particles are thought to be knocked off the surfaces of Jupiter's small, inner moons by micrometeoroid impacts. The rings are therefore constantly being replenished as the dust slowly spirals in toward the planet. They are not a permanent feature, but a dynamic, ever-changing system. Along a steady path, we find a structure made of dust and gentle light. Set the idea down and feel the weight release. The main part of Jupiter's ring system is composed of 3 parts. There is a thick inner torus of particles called the halo, a flat main ring, and 2 wide, even fainter rings called the gossamer rings. The main ring is thought to be sourced from dust kicked off the moons Adrastea and Mede. The gossamer rings are even more interesting. They are aligned with the orbits of 2 other small moons, Amalthea and Thebe. Each moon appears to have its own ring, a wide, diffuse sheet of dust that extends from the moon's orbit all the way down to the main ring. In quieter hours, we see how even the smallest moons contribute to the whole. Let your shoulders drop and the jaw unclench. Beyond the 4 large Galilean moons, Jupiter has a vast collection of smaller, irregular moons. The planet's powerful gravity has captured dozens of asteroids and comets that strayed too close. Most of these captured moons are small, only a few kilometers across, and they follow long, tilted, and highly elliptical orbits. Many of them even orbit the planet backwards, a direction known as retrograde. This is a clear sign that they did not form with Jupiter, but were captured later. They formed distinct families, groups of moons with similar orbits, suggesting they were once part of a larger body that was captured and then broken apart. With simple patience, we can trace the family history of these small captured worlds. Feel the simple ease of being here. Jupiter likely formed very early in the history of the solar system before the other planets. The leading theory, known as core accretion, suggests that a solid core of rock and ice, about 10 to 15 times the mass of Earth, formed first. This core then became massive enough for its gravity to pull in the vast amounts of hydrogen and helium gas that were abundant in the early solar nebula. This process was very rapid, happening over just a few million years. Jupiter grew quickly, sweeping up a huge portion of the material in the outer solar system and becoming the giant we see today. With the same easy pace, the planet came together from a small seed. Let the body be held by what supports you. Some theories propose that Jupiter did not form where it is today. One hypothesis, called the Grand Tack, suggests that Jupiter formed farther out and then migrated inward, coming as close to the Sun as the orbit of Mars. Then, the formation of Saturn farther out created a gravitational resonance that pulled Jupiter back outward to its current position. This grand journey, inward and then outward, would have had a profound effect on the early solar system. It would have scattered the asteroid belt and may have been responsible for delivering water-rich asteroids to the inner planets, including Earth. As the night settles, we imagine the planet's long, slow dance. Rest in the quiet that follows. Jupiter plays an important role as a kind of gravitational guardian for the inner solar system. Its immense gravity acts like a giant shield, deflecting or capturing many comets and asteroids that might otherwise be on a collision course with Earth. We have seen this happen directly, most famously in 1994, when the comet Shoemaker-Levy 9 was torn apart by Jupiter's gravity and its fragments crashed into the planet's atmosphere. While it's not a perfect shield, its presence has likely reduced the rate of impacts on Earth over billions of years, creating a more stable environment for life to evolve. Under quiet skies, a distant giant offers a silent protection. Let that idea rest for a moment before we move on. Even with its protective influence, Jupiter's gravity also stirs things up. The asteroid belt, located between Mars and Jupiter, is a region where a planet might have formed, but Jupiter's gravity prevented it. Its gravitational pull constantly nudges the asteroids, preventing them from coalescing into a larger body. These nudges can also send asteroids careening out of the belt, some of them toward the inner solar system. So while Jupiter protects us from long-period comets, it is also the source of some of the near-Earth asteroids. As you rest, consider this balance of disruption and protection. Nothing urgent here, only a slow and steady pattern. The first spacecraft to visit Jupiter were Pioneer 10 and Pioneer 11 in the early 1970s. They were the first probes to cross the asteroid belt, and they gave us our first close-up images of the planet. They confirmed that Jupiter was mostly liquid, measured its intense radiation belts, and gave us our first look at its polar regions. The data they sent back was fundamental, painting a picture of a world far more dynamic and extreme than we had ever imagined. They were simple probes, but they paved the way for all the exploration that would follow. With unhurried steps, humanity took its first look at the giant. Feel the calm gather around you again. The Voyager 1 and Voyager 2 spacecraft flew past Jupiter in 1979, and their discoveries were revolutionary. They carried more advanced cameras and instruments, giving us stunning, detailed images of the Great Red Spot and the complex, swirling cloud patterns. The Voyagers discovered Jupiter's faint ring system, the first active volcanoes beyond Earth on the Moon, Io. And they provided the first hints of a subsurface ocean on Europa. They were on a grand tour of the outer planets, and their brief flyby of the Jovian system completely reshaped our understanding of it. In this quiet corner, our picture of the solar system changed forever. You can breathe a little deeper and allow the thought to drift. In 1995, the Galileo spacecraft became the first to enter into orbit around Jupiter. For 8 years, it looped through the system, making repeated close flybys of the Galilean moons. Galileo's greatest legacy is its detailed study of these moons. It confirmed the molten interior of Io, provided strong evidence for the oceans on Europa, Ganymede, and Callisto, and revealed Ganymede's unique magnetic field. Galileo also deployed a small probe that plunged into Jupiter's atmosphere, directly measuring its temperature, pressure, and composition as it descended. As the pattern repeats, we get a closer and closer look. Let the thought soften at the edges and fade. The Juno mission, which entered orbit around Jupiter in 2016, is giving us our deepest look yet at the planet itself. Instead of orbiting in the equatorial plane like Galileo, Juno flies in a long, looping polar orbit. This allows it to fly close over the planet's poles, mapping its gravity and magnetic fields with unprecedented precision. It avoids the worst of the radiation belts, allowing it to survive long enough to complete its mission. Each close pass, called a perihove, gathers a trove of data about the planet's interior structure, its deep atmosphere, and its powerful auroras. In a calm rhythm, the probe circles and measures. Settle back into the soft pace of night. Juno's measurements have challenged many of our old ideas about Jupiter. Its gravity data has revealed the fuzzy or dilute nature of the planet's core, suggesting a history of giant impacts. It has peered deep below the cloud tops, showing that the zones and belts, so organized at the surface, dissolve into a more chaotic state deeper down. Juno has also given us our first clear views of the poles, revealing the strange geometric patterns of the polar cyclones. It is painting a portrait of a Jupiter that is more complex, more dynamic, and more beautiful than we ever knew. Through a soft lens, the mysteries of the planet slowly yield. Return to the easy rhythm of your breath. The swirling patterns in Jupiter's clouds are not just surface features. Juno's instruments show that some of these weather systems extend deep into the atmosphere. The powerful jet streams that define the zones and belts, for instance, are not just skin deep. They appear to persist down to a depth of about 3,000 kilometers. At that depth, the pressure is so high and the hydrogen so compressed that it begins to act like a liquid metal, and the organized wind patterns seem to give way to the planet's deeper, more uniform rotation. Beneath the surface, the beautiful chaos of the clouds fades into a simpler, ordered motion. Let that settle like dust on a quiet floor. Jupiter is so large that it does not technically orbit the Sun, at least not in the way the other planets do. Every object in a system orbits a common center of mass, called the barycenter. For a small planet like Earth orbiting the enormous Sun, that barycenter is located deep inside the Sun itself. But Jupiter is so massive that the barycenter of the Jupiter-Sun system is actually located just outside the Sun's surface. So, Jupiter and the Sun both orbit this empty point in space. Jupiter is the only planet in our solar system for which this is true. From a distance, it looks less like a planet orbiting a star, and more like two partners in a slow, graceful dance. Rest in the steady comfort of this moment. The planet's gravity is 2.4 times that of Earth's. If you could stand on a platform in Jupiter's cloud tops, you would feel more than twice as heavy as you do on the ground. An object dropped on Jupiter would accelerate downward much faster. This strong gravity is what allows Jupiter to hold on to its light atmosphere of hydrogen and helium, gases that a smaller planet like Earth would lose to space. It is also the reason that Jupiter's atmosphere is so compressed, achieving pressures at its center that are millions of times greater than the air pressure on Earth. Over time, this gravity has shaped every aspect of the planet. Let your shoulders drop and the jaw unclench. The average temperature at Jupiter's cloud tops is a frigid minus 145 degrees Celsius. This is the temperature of the ammonia clouds that we see from a distance. But because of the planet's internal heat, the temperature rises telluric high inside. At the top of the hidden water cloud layer, the temperature and pressure are similar to that on Earth's surface. Deeper still, where the gas transitions to liquid metallic hydrogen, the temperature is thought to be around 10,000 degrees Celsius, hotter than the surface of the Sun. The core itself may be over 20,000 degrees. In this quiet corner of the solar system, a cold exterior hides a fiery heart. Feel the simple ease of being here. Lawsuits 54. Juno's exploration of Jupiter's magnetic field has revealed it to be even more complex than expected. In the northern hemisphere, the field is strong and uniform. But in the southern hemisphere, it appears much more messy and less concentrated. There is a region of intense magnetic strength, known as the Great Blue Spot, located near the equator. This is not a storm, but a region where the magnetic field lines plunge back into the planet. This asymmetry suggests that the planet's magnetic dynamo, the layer of liquid metallic hydrogen, is not uniform. With unhurried steps, we are mapping the invisible forces that shape the planet. Rest in the quiet that follows. Jupiter is so far from the Sun that it receives less than 4% of the sunlight that Earth does. From the cloud tops of Jupiter, the Sun would appear as a small, intensely brilliant disk, but it would provide little warmth. The planet's weather is not driven by solar heating as it is on Earth. Instead, it is driven by the planet's own internal heat, rising up from its deep interior. This is why the planet can sustain such powerful storms and rapid jet streams. It is a world that makes its own weather, a self-contained engine of atmospheric motion. Under quiet skies, the planet is warmed from within. Let an idea soften at the edges and fade. When the Galileo probe descended into Jupiter's atmosphere in 1995, it made a surprising discovery. It found that the region it entered was much drier than expected, with very little water. For years, this was a puzzle, but scientists now believe the probe just happened to enter a hot spot, a relatively cloud-free region where dry gas from deep within the atmosphere is rising. These are the Jovian equivalent of deserts. They are a feature of Jupiter's belts, the darker bands where gas is generally sinking. These small, dry patches are not representative of the planet as a whole. Along a steady path, we learn that one measurement is not the whole story. Nothing urgent here, only a slow and steady pattern. Io's gravitational relationship with Jupiter and its neighboring moons is a delicate and precise dance. For every one orbit that Ganymede completes, Europa completes 2. And for every 2 orbits Europa completes, Io completes 4. This is known as a Laplace resonance. This regular repeating pattern of gravitational tugs is what prevents the moon's orbits from becoming perfectly circular. It constantly forces them into slightly elliptical paths, which is the ultimate source of the tidal heating that powers Io's volcanoes and keeps Europa's ocean liquid. In the gentle background, an orbital rhythm creates warmth and change. Allow the day to fall away now. The chaos terrains on Europa are some of its most intriguing and mysterious features. These are areas where the icy crust appears to have been broken, rotated, and frozen back into place, like icebergs in a frozen sea. Scientists believe these regions may form over pockets of warmer, rising slush or water from the ocean below. The surface ice collapses and fractures, creating a jumbled, chaotic landscape. These areas are thought to be some of the youngest and most geologically active parts of Europa's surface, and they are prime targets in the search for any signs of the ocean's chemistry. In quieter hours, we find beauty in the broken and rearranged patterns. Let your breathing find a slower pace. Ganymede's surface is a stark contrast of old and new. The dark, ancient terrains are saturated with craters, some of which are so old that they have relaxed and flattened over billions of years, leaving behind faint circular outlines called palimpsests. In contrast, the younger grooved terrains are marked by long, parallel sets of ridges and valleys. These grooves may have formed as the moon's crust was stretched apart by tectonic forces, allowing cleaner ice from below to fill in the gaps. This history of resurfacing has erased many of the craters in these regions, giving them a much younger appearance. With simple patience, we can read the moon's history in its surface textures. Hold only the calm and let the rest drift. The reason Callisto is so different from the other Galilean moons is likely its distance from Jupiter. Being the farthest out, it experiences the least amount of tidal heating. This means it cooled down much faster after its formation and never developed the same level of geological activity as its siblings. It does not have enough internal heat to power volcanoes or large-scale tectonics. As a result, its interior never fully differentiated, meaning the rock and ice never cleanly separated into a core and mantle. It remains a more primitive mixed body, a frozen snapshot of the early days of the solar system. With the same easy pace, we see how proximity to warmth changes everything. Feel the calm gather around you again. One of the most powerful volcanic plumes on Io, named Pele, creates a huge, persistent red ring on the surface. The plume itself is a towering fountain of sulfur dioxide gas and dust, rising 300 kilometers high. As the material falls back down, it coats the ground in a giant, distinctive circle, more than 1,000 kilometers in diameter. The red color is thought to be from various forms of sulfur, some of which are created as the plume material rains down and settles. This red ring is one of the largest and most easily identifiable features on Io's ever-changing face. As the night settles, a volcanic fountain paints a silent red circle on a distant moon. Let the body be held by what supports you. Jupiter has Trojan asteroids, two large groups of space rocks that share its orbit around the Sun. One group, the Greeks, travels ahead of Jupiter, and the other, the Trojans, travels behind. They are clustered in gravitationally stable regions known as Lagrange points. These asteroids are not moons, as they orbit the Sun, not Jupiter, but they are trapped in a one-to-one resonance with the giant planet. There are thousands of them, and they are thought to be ancient remnants from the formation of the solar system, containing clues about the earliest building blocks of the planets. Elsewhere in this picture, we find fellow travelers on the planet's long journey. You can breathe a little deeper and allow the thought to drift. While Saturn is famous for its bright rings, Jupiter, Uranus, and Neptune all have ring systems too. They are just much darker and fainter. The particles in Jupiter's rings are very small, like the dust in a sunbeam. Because of this small size, they are easily pushed around by sunlight and by Jupiter's magnetic field. This causes the innermost halo ring to be puffy and donut-shaped rather than flat. The dust particles don't last long. They are either pulled into Jupiter or ejected from the system. The rings only exist because they are constantly being resupplied with new dust from the inner moons. Without any hurry, a balance is maintained between loss and creation. Let that idea rest for a moment before we move on. Amalthea is the largest of Jupiter's inner moons and the reddest object in our solar system. It is a small, potato-shaped moon, about 250 kilometers long. Its deep red color is a mystery. It is likely caused by sulfur compounds ejected from the volcanoes of Io, which then spiral inward and coat Amalthea's surface. The moon is tidally locked to Jupiter, meaning the same side always faces the planet. It is also losing heat, radiating slightly more energy than it receives from the Sun, possibly due to a small amount of tidal flexing or its own leftover formation heat. Through a soft lens, we see a small red world in the shadow of the giant. Set the idea down and feel the weight release. The wind speeds on Jupiter are some of the fastest in the solar system. The jet streams that separate the zones and belts can reach speeds of over 540 kilometers per hour. These winds are not just confined to the upper atmosphere. Data from the Juno mission suggests that they penetrate thousands of kilometers down. Unlike winds on Earth, which are driven by solar heating, Jupiter's winds are powered by its internal heat, escaping from the deep interior. This makes the weather system incredibly stable and powerful, a global engine of wind that has run for billions of years. In a calm rhythm, the planet's breath blows in great, powerful currents. Let your shoulders drop and the jaw unclench. When observers first carefully documented it in the late 1800s, it was described as a striking brick red. In the 1970s, Voyager images showed it as a paler, more orange hue. More recently, its color has deepened again. Scientists think this might be tied to the storm's intensity. When the storm's winds are stronger, its central updrafts might be more powerful, dredging up more of the color-creating chemicals from deeper inside and lifting them to higher altitudes where sunlight can change them. As the pattern repeats, the storm's color gently breathes and shifts. Feel the simple ease of being here. Despite the intense radiation, the swirling storms, and the lack of a solid surface, some have speculated about the possibility of life in Jupiter's atmosphere. The scientist Carl Sagan once proposed the idea of floating, balloon-like creatures, floaters, that could live in the temperate layers of Jupiter's clouds. He imagined them feeding on organic molecules or even on smaller airborne life forms. There is no evidence for such creatures, and the strong vertical winds would make it very difficult for any life to avoid being carried down to lethal depths. But it remains a gentle, imaginative thought. As you rest, imagine life in a place with no ground. Return to the easy rhythm of your breath. The polar regions of Jupiter, which we have only seen clearly with the Juno spacecraft, do not have the organized bands of the lower latitudes. Instead, they are a beautiful, chaotic-looking mix of smaller storms and vortices. The color is a deep, dramatic blue, speckled with the bright white pop-up clouds of small storms. This deep blue color is likely due to us seeing a clearer, less hazy view of the deeper atmosphere. The large, persistent cyclones of the poles are a mystery, as is why they arrange themselves into such stable geometric patterns. Under quiet skies, the poles of the planet show a different, bluer face. Let that settle like dust on a quiet floor. Jupiter's moon, Europa, has a very thin atmosphere, composed mainly of oxygen. But this is not an oxygen created by life. It's produced by a process called radiolysis. As the intense radiation from Jupiter's magnetosphere bombards the moon's icy surface, it splits the water molecules into hydrogen and oxygen. The lighter hydrogen gas escapes into space, while the heavier oxygen is retained, forming a tenuous atmosphere. Some of this oxygen may find its way down into the subsurface ocean, which could be a vital ingredient for any potential life there, providing a way for organisms to metabolize without sunlight. From a distance, we see how radiation can create a molecule essential for life. Rest in the steady comfort of this moment. The day-night cycle on Jupiter's moons is extreme. Because they are tidally locked, they keep one face permanently turned toward Jupiter. This means that Jupiter hangs in the same spot in their sky, never rising or setting. For an observer on the Jupiter-facing side of Europa, the giant planet would dominate the sky, appearing more than 20 times wider than our full moon. It would go through a full cycle of phases, from a thin crescent to a blindingly bright full Jupiter, every 3.5 days. On the far side of the moon, Jupiter would never be seen. In this quiet corner, the sky is dominated by the parent planet. Settle back into the soft pace of night. The volcanic plains of Io are home to features called paterae. These are large, caldera-like depressions with flat floors and steep walls. They are not all volcanoes themselves, but they are often the source of vast, dark lava flows that spread for hundreds of kilometers. The largest of these, Patera, is a 200-kilometer wide lake of molten lava, covered by a thin, dark crust. This crust periodically breaks and founders, leading to a massive overturning of the lava lake and a huge increase in its thermal emission. This regular brightening makes Patera one of the most powerful and predictable volcanoes on Io. Along a steady path, a lava lake quietly overturns and glows. Hold only the calm and let the rest drift. Ganymede's grooved terrain is a complex landscape. The grooves are long, parallel sets of ridges and troughs, and they can run for thousands of kilometers. They often cut across each other, allowing scientists to work out their relative ages. It is thought that this terrain formed when Ganymede's crust was stretched and fractured by tectonic activity long ago. As the crust pulled apart, cleaner ice or even liquid water from the interior welled up to fill the gaps, creating the brighter, younger surface. This process of expansion and resurfacing seems to have happened in several episodes, creating a complex and layered geological history. With simple patience, we can unwind the story of the moon's surface. Let the thoughts soften at the edges and fade. Jupiter's rings are not the only source of dust in the Jovian system. Every one of its moons is constantly being bombarded by micrometeoroids. This sandblasts tiny particles of dust off their surfaces. This dust then goes into orbit around Jupiter, creating a vast, tenuous cloud. The entire Jovian system is filled with this fine dust, though it is far too thin to be seen with the naked eye. This process also means that the moons are subtly exchanging material with each other. Dust from Io can end up on Europa, and dust from Europa can end up on Ganymede, slowly mixing the chemistry of the system over billions of years. Over time, everything is shared. Allow the day to fall away now. The small innermost moons, Aradrastia, Metis, Amalthea, and Thebe, are all tidally locked and orbit very close to Jupiter. They are all inside Jupiter's Roche limit, the distance within which a planet's gravity is strong enough to pull a moon apart. The only reason they survive is that they are small and solid enough to be held together by their own material strength. They orbit so fast that they circle Jupiter in less than one Jovian day. This means that if you were at Jupiter's cloud tops, you would see these moons rise in the west and set in the east, moving faster across the sky than the planet's own rotation. With the same easy pace, we find moons that outrun the planet's own spin. Nothing urgent here, only a slow and steady pattern. Jupiter's faint gossamer rings are unusual. There are 2 of them, and they are associated with the orbits of the small moons, Amalthea and Thebe. The rings are thickest at the moon's orbits, and then they spread inward. They are also vertically thick, puffing up far above and below the main ring plane. This strange shape is caused by the moon's own tilted orbits. As the moons travel on their inclined paths, their dust trails are slowly spread up and down by Jupiter's gravity. The resulting ring is a ghostly wedge-shaped sheet of dust, fainter than the main ring but much larger in volume. In the gentle background, dust forms a ghostly and beautiful shape. Feel the calm gather around you again. Callisto's surface is one of the most ancient landscapes we have ever seen. Because the moon has had so little geological activity, its surface has preserved a record of impacts stretching back 4 billion years. It is saturated with craters, meaning that any new impact is more likely to erase an old crater than to hit a fresh patch of ground. This makes it an invaluable window into the late heavy bombardment, a period in the early solar system when the rate of asteroid and comet impacts was much higher. Callisto is a quiet historian, its face scarred with the memory of a more violent time. In quieter hours, we can listen to the stories told by ancient silence. Let your breathing find a slower pace. Unlike the other Galilean moons, Callisto is not in an orbital resonance. Its orbit is not locked in a simple mathematical ratio with Ganymede, Europa, or Io. This is another reason why it experiences so little tidal heating. It is too far from Jupiter, and its orbit is too circular to be significantly squeezed and flexed. This lack of heating is the key to its history. It allowed the moon to freeze a lid early on, and it prevented a full separation of its rock and ice interior. Callisto is a control sample, a vision of what the other moons might have been like without the constant, gentle massaging of Jupiter's gravity. With unhurried steps, we understand the importance of a rhythmic dance. Let that idea rest for a moment before we move on. The Galileo probe's descent into Jupiter's atmosphere ended when the probe was crushed by the immense pressure. It sent back data for about an hour as it fell, reaching a depth of about 150 kilometers below the cloud tops. In its final moments, it measured temperatures of over 150 degrees Celsius and pressures 22 times that of Earth's sea level. It was a one-way trip, designed to gather as much data as possible before the planet's atmosphere inevitably destroyed it. The mission's end was a deliberate plunge into Jupiter to ensure the spacecraft could never accidentally crash on and contaminate the moon. Europa. Without any hurry. No stamos un proposito a te alfim. Let your shoulders drop and the jaw unclench. The Juno spacecraft's orbit is highly elliptical. It spends most of its 53-day orbit far away from Jupiter, in the safer, less radioactive regions of space. Then, for just a few hours, it dives in, flying fast and low over the planet's poles, gathering its data in a brief, intense burst. This strategy allows the spacecraft to get incredibly close to the cloud tops, just a few thousand kilometers above them, while minimizing its exposure to an otherwise lethal dose of radiation. This looping, polar orbit is the key to the mission's success and its longevity. As the pattern repeats, the probe makes its daring dive again and again. Hold only the calm and let the rest drift. The pearls of Jupiter are a string of large, white, anticyclonic storms found in a single jet stream in the southern hemisphere. There are usually between 6 and 9 of them, spaced out fairly evenly. They are long-lived features, though they do occasionally merge or dissipate. They have been observed for decades, a necklace of white ovals adorning one of the planet's southern belts. They are smaller than the Great Red Spot, but they are still enormous storms, each one large enough to swallow smaller planets. They are another example of the long-term stability and order that can emerge from Jupiter's chaotic-looking atmosphere. Through a soft lens, we see a string of pearls on the giant's cloak. You can breathe a little deeper and allow the thought to drift. The Eoplasma Taurus, that donut of ionized gas fed by Eo's volcanoes, plays a huge role in powering Jupiter's auroras. As Jupiter rotates, its magnetic field sweeps through this torus, accelerating the particles to high speeds. Some of these energized particles are then funneled down the magnetic field lines toward Jupiter's poles, where they slam into the atmosphere and create the bright auroral glow. In this way, Io and Jupiter are linked by an invisible circuit. The moon provides the raw material, and the planet's rotation provides the energy to create the most spectacular light show in the solar system. As you rest, imagine this invisible connection between a moon and its planet. Let the body be held by what supports you. Europa's chaos terrain is not just a jumble. Up close, It looks as though large pieces of the icy crust have broken away, moved, and rotated like rafts of ice, before being frozen back into a new position. Scientists have been able to digitally reconstruct some of these areas, cutting out the pieces and moving them back to their original positions, like a jigsaw puzzle. The fit is often remarkably good. This provides strong evidence that a liquid or slushy layer exists just beneath the surface, decoupling the crust and allowing these large blocks to float and drift before refreezing. In this quiet corner, a frozen surface tells a story of a liquid past. Feel the simple ease of being here. The auroras on Ganymede are unique. They are created not just by Jupiter's magnetic field, but by the interaction between Jupiter's field and Ganymede's own personal magnetic field. As the two fields connect and disconnect, they create a rocking motion in the auroral oval. By studying the amount of this rocking, astronomers were able to deduce the presence of a salty ocean beneath the ice. The ocean's electrical conductivity damps the rocking motion, acting as a kind of brake. The amount of damping told them how deep the ocean was and how salty it must be. Along a steady path, a light in the sky reveals an ocean in the deep. Let the thoughts soften at the edges and fade. The impacts on Callisto are so old that the ice has had time to flow. Over billions of years, even solid ice behaves like a very slow-moving fluid. This has caused the oldest and largest craters on Callisto to relax and flatten. Their rims have subsided and their floors have risen, leaving only a faint circular marking, a ghost of the original impact. These ancient faded craters are known as palimpsests. They are a testament to the immense age of Callisto's surface and the slow, patient work of time, which can eventually flatten even the most dramatic scars. From a distance, the moon's face is a soft record of ancient blows. Rest in the steady comfort of this moment. The Himalaya group is a family of small, irregular moons that orbit Jupiter at a great distance. They are all thought to be fragments of a single asteroid that was captured by Jupiter's gravity and then shattered by a collision. There are 5 known members of the group, with Himalaya being the largest. They all have similar prograde orbits, meaning they circle Jupiter in the same direction as its rotation. Their dark reddish color suggests they are primitive C-type asteroids, rich in carbon. They are like a broken family, traveling together on a long, looping path around the giant planet. Over time, even broken pieces find a shared path. Let that settle like dust on a quiet floor. The planet's immense gravitational field can act as a lens. When a distant star or galaxy passes directly behind Jupiter, its light can be bent and magnified by the planet's gravity. This phenomenon, called gravitational lensing, was predicted by Einstein's theory of general relativity. While Jupiter's effect is small, it is measurable. In a similar way, Jupiter's atmosphere can bend starlight, allowing us to study its composition. As a star passes behind the planet, its light shines through the upper atmosphere, and by analyzing the spectrum of that light, we can see what gases are present. Without any hurry, the planet itself becomes a tool for seeing. Settle back into the soft pace of night. Fact tiny. 87 Juno has shown that the ammonia in Jupiter's atmosphere is not evenly mixed. It seems to form a weather layers that is much more variable than what is beneath it. There are places where the ammonia is enriched and places where it is depleted. This variability seems to be linked to a kind of Jovian hail, or mush balls, made of ammonia and water. These mush balls form in the upper atmosphere, grow heavy, and then fall, carrying the ammonia down into the deep atmosphere. This process cleanses the upper layers of ammonia in some regions, creating the variability that Juno observes. In the slow turn of the planet, a strange kind of hail shapes the weather. Return to the easy rhythm of your breath. The upcoming Europa Clipper mission is designed specifically to investigate Europa and its potential for life. It will not orbit Europa directly, as the intense radiation there would quickly destroy the spacecraft. Instead, it will orbit Jupiter and make dozens of close, fast flybys of the icy moon. During each flyby, it will use a suite of advanced instruments to study the ice shell, confirm the presence of the ocean, search for and sample any plumes, and map the moon's surface in high resolution. It will be our most detailed look yet at this tantalizing world. With simple patience, we are preparing for our next visit. Let that idea rest for a moment before we move on. Jupiter has no seasons in the way that Earth does. Seasons on Earth are caused by the tilt of our planet's axis. As we orbit the Sun, first one hemisphere and then the other is tilted toward it, creating summer and winter. Jupiter's axis, however, is tilted by only about 3 degrees, barely any tilt at all. This means the amount of sunlight hitting any given part of the planet is very consistent year-round. Jupiter's long 12-year orbit doesn't bring it much closer or farther from the Sun. The planet's climate is therefore remarkably stable over time, driven by its internal heat, not by the changing seasons. Under quiet skies, the weather follows its own internal clock. Feel the calm gather around you again. The Great Red Spot is a high-pressure system, which means air is sinking in its center. Or so we thought. But recent observations of the storm's temperature show that the center of the storm is actually warmer than its surroundings, which is a signature of rising gas. This has created a puzzle. The storm spins like a high-pressure system, but its thermal structure looks like a low-pressure system. It seems to have a complex three-dimensional structure, with both rising and sinking motions in different parts of the storm. As we get a closer look, the simple picture becomes more beautiful and more complex. As the night settles, we learn that even a storm has its quiet complexities. You can breathe a little deeper and allow the thought to drift. Jupiter's moon. Europa is covered in ridges, but it also has double ridges. These are pairs of parallel ridges with a central valley between them. They are just as of the most common features on the moon, stretching for hundreds of kilometers. Scientists are still not sure how they form. One idea is that they are created as the ice shell cracks and slushy ice from below is squeezed up and deposited on either side of the crack. Another idea is that they form over small liquid water sills just beneath the surface. Whatever their origin, they are a sign of the constant stress and fracturing of Europa's dynamic ice shell. In this quiet corner, the ice is constantly being reshaped. Let your shoulders drop and the jaw unclench. The Cassini spacecraft, on its way to Saturn, flew by Jupiter in the year 2000 and provided a unique opportunity. For a few weeks, both Cassini and the Galileo orbiter, which was already at Jupiter, were able to observe the planet at the same time. This allowed for joint observations, with one spacecraft getting a close-up view while the other saw the bigger picture. They were able to track storms, watch the interaction of the solar wind with the magnetosphere, and create some of the most detailed global movies of Jupiter's atmosphere ever made. It was a brief, coordinated dance of two robotic explorers. With unhurried steps, we learn more when we look from multiple perspectives. Hold only the calm and let the rest drift. If you were to fall into Jupiter, you would not hit a solid surface. You would just keep falling through denser and denser layers of gas. The pressure and temperature would steadily increase. After passing through the ammonia, ammonium hydrosulfide, and water cloud layers, you would enter the deep, clear atmosphere of hydrogen and helium. Eventually, the pressure would become so great that the gas would compress into a liquid. But the transition would be gradual, with no surface to splash into. You would simply find yourself in an increasingly dense, hot, and dark ocean, continuing to sink toward the planet's exotic core. As you rest, let go of the need for solid ground. Feel the simple ease of being here. The auroras on Jupiter are not only powered by the solar wind and by material from Io. They are also, in part, powered by the planet's own rotation. Jupiter's magnetic field spins with the planet, and this spinning field drags charged particles along with it. This process acts like a giant particle accelerator, generating some of the energy that creates the auroras. This is different from Earth, where our auroras are almost entirely powered by the sun. Jupiter's auroras are a hybrid, driven by both external and internal forces, a manifestation of the planet's immense rotational energy. Along a steady path, we find a light show powered by the planet's own spin. Rest in the quiet that follows. The Voyager spacecraft are now in interstellar space, but they carry a memory of Jupiter with them. On board each spacecraft is a golden record, a gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. It is a message in a bottle, a greeting to any extraterrestrial civilization that might one day find it. The records also contain a sound recording of Jupiter's radio emissions, the crackle and hiss of its magnetosphere. It is a recording of the planet's own voice, a faint, rhythmic static now traveling silently through the space between the stars. In the gentle background, the planet's song travels onward. Let that idea rest for a moment before we move on. Ganymede's groove terrain often appears to be tectonically related to its older, darker terrain. In many places, it seems that large blocks of the dark terrain have been pulled apart, with the bright groove terrain filling the space between them. This suggests a process of rifting, similar to what happens on Earth when continents pull apart. It is a sign of a time when Ganymede was more geologically active, when its crust was being stretched and reshaped by internal forces. The moon's surface is not just two different types of terrain, but a dynamic story of how one grew out of the other. Through a soft lens, we see a story of expansion and renewal. Let the thought soften at the edges and fade. The swirling storms at Jupiter's poles are not like hurricanes on Earth. Hurricanes are powered by warm ocean water, and they die out when they move over land. Jupiter's polar cyclones are powered by moist convection, the release of heat when water vapor condenses and freezes. They are also incredibly stable, lasting for years without moving much. The geometric patterns they form, a pentagon in the south and an octagon in the north, are a result of complex fluid dynamics, a kind of self-organizing pattern that emerges in a rotating system. Over time, even in a chaotic system, a kind of order can appear. Let the body be held by what supports you. The hot spots in Jupiter's belts, the dry, cloud-free areas, are surrounded by turbulent, cloudy regions. The imagery from our spacecraft shows that these hot spots are not calm. They are often the site of active storm formation, with bright white clouds bubbling up along their edges. It seems that while the hotspots themselves are areas of sinking, dry air, their interaction with the surrounding moist atmosphere is a trigger for convective storms. They are not just deserts, but the edges of oases, regions where the contrast between dry and wet air fuels new weather. As the pattern repeats, we see that even the driest places can be a source of storms. Settle back into the soft pace of night. Io's volcanoes are not all the same. Some, like the Pelée Plume, are tall, umbrella-shaped fountains that last for months or years. These are thought to be powered by the explosive release of sulfur dioxide gas. Other eruptions are more like the lava flows on Earth, with molten silicate rock pouring out onto the surface. These flows can be vast, covering thousands of square kilometers. They are hotter and less frequent than the sulfur plumes. Io's volcanism is complex, with different styles of eruption happening at the same time, all driven by the relentless rhythmic squeeze of Jupiter's gravity. In a calm rhythm, a world expresses its inner heat in many different ways. Allow the day to fall away now. The New Horizons spacecraft, on its way to Pluto, used Jupiter for a gravity assist in 2007. It flew past the planet to steal a little of its orbital energy and get a speed boost for its long journey to the outer solar system. It was a fast flyby, but it gave us our best look yet at the little red spot, as well as new views of the faint rings and the smaller moons. It also captured a spectacular movie of a volcanic plume erupting from Io's surface, rising and falling against the backdrop of space. It was a fleeting visit, a brief pause on a longer journey, but it added another layer to our understanding of the giant. With the same easy pace, we used the giant's own gravity to explore even farther. Nothing urgent here, only a slow and steady pattern. Jupiter's presence has shaped the very architecture of our solar system. Its rapid growth in the early days dictated how much material was available for the other planets to form. Its migration may have cleared out the region where Mars is, explaining why Mars is so much smaller than Earth. Its gravity sculpted the asteroid belt and continues to send a steady stream of comets and asteroids into the inner solar system. We live in a solar system that is defined by Jupiter. It is not just another planet. It is a foundational piece of our cosmic home, a quiet, distant giant whose gravity has been our shepherd and our shield. In this quiet corner, we are all part of Jupiter's family. You can breathe a little deeper and allow the thought to drift. And so our journey through the Jovian system comes to a gentle close. We have drifted through clouds of ammonia, witnessed storms older than nations, and imagined the dark, silent oceans of the Galilean moons. We have seen a world of immense scale and subtle beauty, a planet that makes its own heat and a family of moons warmed by a gravitational dance. Jupiter is a reminder of the quiet power that shapes our universe, the steady pull of gravity, the slow march of time, and the dance of chemistry and light. As you settle deeper into your rest, you can let these thoughts go. They will continue on their own, just as Jupiter continues its long, slow orbit around the distant sun. You can simply rest now, a small, warm presence in a vast and peaceful universe. There is nothing left to do but drift. Sleep well. Good night.